Good morning, everyone. I'm Vinish. I'm a PhD student in Department of Electrical Engineering, IIT Bombay. I'll be presenting our paper on generation of effective guidance hints for better design debugging by formal methods. We'll start with the introduction, and then we'll go to the motivation behind the work, and then we will talk about our proposed methodology, and then we have conducted some experiments on messy coherence protocol, which we'll discuss after that, along with the results, and then the observations which we have from the experiments, and then we'll conclude the presentation. For verification, there are verification and debugging. There are two broad approaches. One is simulation based, and another is formal methods. So the simulation based methods are not very practical to do full verification and debugging because of the exhaustive limitation in the exhaustive simulation, which is not possible. And for debugging, using the traces will be not very feasible because of the size of the simulation traces. So if we go for formal methods, the counterexamples can provide better debugging hints. And then if we use guidance based model checking for formal methods, then we can get counterexamples in shorter time, and then tackle the issue of state space explosion in typical formal method. As I discussed, state space explosion is a major problem in using formal methods for design debugging. And then in the tools which are available have very limited bound which can be used for debugging. So our objectives here is to use is to debug design errors on the simulation trace using the guidance hints which will be used by the model checker. So we'll be working on generation of the hints and then ensuring the quality of those hints to make sure that bounded model checker takes lesser time compared to the case where we don't have any hints. So here we introduce the concept of waypoints. So waypoints are nothing but a set of signals which is fully or partially specified with data values. And these signals along with the data values correspond to a set of states which we call gate post. In the cone diagram, this is a state space traversal diagram. If we are using waypoints to reach the target state T, which is on the rightmost side, then you will be covering only the green areas in the state space. Unlike the case where you don't have waypoints, where you would be covering much larger area, consuming good amount of time. There has been some works in waypoints. One was for debugging an actual design error in a real chip with 33 million gates. And then the second one was for verification, where they were trying to reach the waypoints using SAT based model checker. In that paper, they were also getting help from the simulation. And then they were using simulation to find out the initial states from where they need to start to reach future waypoints from a particular waypoint. To understand the concept of waypoints and to get a feel of what actually happens, we conducted a small experiment with four 13-bit counters which counts in different steps. And then we used a property which is as shown in the slide, that any value of any counter exceeding the value 8188, which is like one step before the stage where the counter fastest counter becomes full. So if we are then we selected four set of waypoints. So in the first case, we considered only one waypoint, which is the half value of the counter for the counter 4. And then subsequently, we considered multiple waypoints, which are equidistant count values of the fastest counter. So the results are shown in the table. So if we don't use any waypoint, which is the first row of the table, we will be getting 224 seconds for checking the property. I mean, getting the counter example from the property. compared to the last case, the row 4, where you have 4 waypoints and you get a total time of 51 seconds, which is a significant reduction in BMC time compared to the case where we didn't have any waypoints. Now we move on to the proposed methodology. So the objectives and or the focus areas here are the identification of waypoints in a large and complex design. And second part is to evaluate the quality of the waypoints. And then the third challenge is to identify, once you have good quality waypoints, identify the starting states for traversal to the next gate post. In this diagram, in this slide, we have the entire workflow. We start with the error trace from the RTL simulation, and then we analyze the trace, and then we come when we come up with a certain assumptions on the buggy areas where the bug could be present, and then we formulate a set of properties which satisfies our assumption. For example, if the bug is in a particular area, then the property will give a counterexample. And then we start the actual process by target finding a set of target signals from the property, and then we construct something called signal dependency graph, and then we do reductions in the signal dependency graph based on the hints from the property, and then we identify a set of candidates for the waypoints, and then we shortlist certain signals from the candidates, and then there's a major part where we assign data values to those signals, and then those are called waypoints. So in that algorithm, we discussed something called signal dependency graph. And in this slide, you will find an example of a signal dependency graph. This is for a simple FIFO. If you take target signal as status full signal of the FIFO, this would be how the signal dependency graph look like. So there are it's a directed graph, and wherever you find an edge, that means there is a direct dependency between those two signals. Now we'll explain the algorithm with a case study. In our experimental setup, we have used messy coherence protocol. So this coherent system ensures consistency between different copies of data with same memory address. And this is widely employed in performing coherence maintenance tasks in systems with multiple masters having local caches. There are 4 states in which each cache lane can be modified, exclusive, shared, and invalid. And there are 2 buses, main bus and coherency bus in the protocol. So the bug which we have introduced in the design is the following. So in there are 4 BRIC FIFOs, which are the FIFOs which gets requests from different CPUs, requests for read and write into the memory in the caches. So we have introduced a bug in the FIFO 2 such that even when the FIFO 2 is full, it will not make its status full signal high. So which will result in accepting more data to the FIFO 2, overwriting the last entry. So we start with actual manifestation of the bug from the simulation trace, which is occasional misses of requests from CPU 2. Occasional because this will happen only when FIFO 2 is full. That's what makes it more interesting, and that's what makes it more like a corner case bug. Moving to the second part of the algorithm where we formulate the property, we have to come up with certain assumptions on where the bug could be. So this is an iterative process, and iterative process where we keep on testing various assumptions. So here is an example where you assume that there is a bug in FIFO 2. There can be bug in FIFO 1, there can be bug in FIFO 3 and 0. So we'll discuss the case where we have bug in FIFO 2 because this is the case which is going to succeed. So in this case, where we feed requests from CPU 0, 2, and again another request from CPU 0. And the second part of the property is where these requests are getting forwarded to the broadcast FIFO. As you can see, we have written in such a way that requests from CPU 2 are getting missed. And subsequently, in the third part of the property, last 4 lines, the control signals are generated corresponding to only the requests which are getting forwarded. So what it means is that if you have the property getting satisfied, then your assumption about the bug is correct. Now we get target signals from the property which are the last structurally near to the primary output of the design, which are CBus CMD0O and CBus address O. In the step 3, we had generated a signal dependency graph for those target signals, VLR2 signal dependency graphs. And then now we derive certain hints from the signal dependency from the property for reducing those signal dependency graphs, because this will contain a large number of signals from the design. So it seems that CPU 1 and CPU 3 does not affect checking of the property. So the SDG can be sliced to remove areas where you have requests coming from CPU 0. So this will be BRIC FIFO 0 and 3, which will be removed from the signal dependency graph. Now we come up with a set of signals which can be potential waypoints. So as a simple strategy, we remove just clock and reset signal from the signal dependency graph. Now we find longest n paths in the signal dependency graph and divide them into 3 sections so that we get 2 waypoint clusters. So some example sample signals from group 1 and 2 are stateful and right pointed, and then data output of the broad FIFO. Now data values are assigned manually by looking at the design. This is a broad research area and we have done this part manually. And these are the values which made sense for checking of the particular property. Now we'll discuss the experimental results. As discussed earlier, we get significant speed up in checking the real property when we have waypoints. Total time taken without waypoint was roughly 7,947 seconds, and then with waypoints, all the 3 sections combined was taking around 694 seconds. And then we repeated the experiment with different size for the broadcast FIFO. So there was a second experiment with another bug introduced in the priority logic, which would again mask the request from broadcast FIFO 2, BRIC FIFO 2, and then it won't be reaching broadcast FIFO because of the bug. Again, we can have similar property for various assumptions about buggy regions and repeat the process along with waypoints and then observe the timing. So So this case was more interesting because without waypoint, model checker was giving a timeout. With waypoint, we were able to prove the property in around 215 seconds. So this process experiment was repeated for another broadcast before size, and then one trend was when we increase the broadcast before size, the time was coming down. That is a particular nature of the design. Summary. So we have proposed a methodology, rather a framework for identifying waypoints for design debugging in large designs, and we have obtained waypoints which led to quicker model checking, and most importantly, we have came across certain challenges, rather future options for future research, which is assigning data values for waypoint signals and reducing significantly the number of waypoint signals. Thank you for listening.